So let's put a substituent on the diene, like a methoxy group, which is electron donating, right? And it can actually donate electrons not just inductively by hyperconjugation, but by real conjugation. We can write a resonance structure for this guy. It looks like this. It actually has a double bond to the oxygen. So that is a better electron donor than just the plain old methyl groups that we had before. And I'm going to leave the CH3 groups on here, just so we can keep track of the inner and the outer positions by having them be different. So we've raised the HOMO energy even more by putting another electron donating substituent on there. Actual resonance like this through a pi system is a more powerful electron donor than pure hyperconjugation. Conjugation is better. Hyperconjugation is like conjugation light. Doesn't work as well. The dienophile that we had, which had that one, the dienophile that we had, which had this oxygen, also has the ability to write a resonance structure. Actually, it's got the ability to write a couple of different resonance structures. Like this one. But that turns out not to be the resonance structure that's going to explain our regiochemistry. The resonance structure that's going to explain our regiochemistry is the one where we involve the other pi bond as well. You'll notice that I've drawn the aldehyde in the endo position pointing towards the diene, right? That stereo is selected for that in the secondary orbital overlap. And you'll notice that I drew the aldehyde here, so it was kind of on the opposite side of the ring to where the methoxy group was. That's favorable. So the product of this reaction is going to put the aldehyde and the methoxy in a 1,4 relationship. Rather than the other possible stereochemistry, something like that. So this one is not formed as much. Should the methyl groups be up or down? It's not as easy to see that from this type of drawing. It's much easier to see it from this type of drawing. Sticking out, down or up?
Down.
Down, same. Right. We have to change that here. The CH2 groups are still down, they're still cis to each other because they're both in the E position or the Alder position. Should the aldehyde be up or down?
Down as well.
Down as well because it's the endo position. Down, like this. So with all the stereochemistry in place, it looks like that. And the 1,4 is preferred. Why is the 1,4 preferred? Because this negative end of the diene wants to get together with this positive end, the dienophile. So that bond is going to form, that's the sigma bond. This oxygen is going to come back in and donate its electrons. That's going to help push this over to form the other sigma bond. And then this guy's going to come in like this and shove those electrons back onto the methoxy. So there's more electrons flowing here. But it's the fact that the aldehyde pulls electron density away, thus putting a significant partial positive charge on this end. And the methoxy group donates electrons, putting a significant partial negative charge on this end. Getting that partial negative together with that partial positive is favorable. And we don't have that interaction with this end, right? This end doesn't really have a partial negative on it. So the 1,4 stereochemistry is preferred if you have a electron donating substituent on the back end of your diene. If you were to have an electron donating substituent on the end of the diene like this, the product would end up forming the 1,2 stereochemistry, where the methoxy group and the aldehyde instead of the 1,3. So basically, the 1,3 is never fixed. It's either going to be 1,4 if the electron donating substituent is on the internal part of the diene, or it's going to be 1,2 if the electron donating substituent is on the end of the diene. And we're talking here about substituents that can donate electrons not just inductively, but by resonance. So they have lone pairs. So why? And you'll see I put it in the endo position, right? Endo goes down, and then the outer substituent, because of the way that rotates, that this rotatory motion, it goes down as well. It would be the exact opposite if instead of bringing the dienophile underneath the diene like this, I brought it on top. There's absolutely no difference between this because they're both planar. This interaction and this interaction are equally favored. If I brought it from the top, you'll notice that this rotatory motion would now put the two methyl groups up, and the secondary orbital overlap would still be there, and then when that rotated, the aldehyde would also be up. So I get a racemic mixture in both cases. The stereochemistry is still the same, right? The outer substituents still end up on the same side as the endo, and the inner substituents still end up on the same side as the exo. But everything is reversed. So why is the 1,2 preferred? How can I explain the fact that the 1,2 interaction is the one that we want? Other than by memorizing it. Memorizing it is good. Memorizing it only gets partial credit. What method did I use to explain it when the methoxy group was here? So I'm probably going to use resonance. So what I want to do is figure out the resonance structure of this that has that charge separation. I'm going to push this pair of electrons in to form the carbon-oxygen bond. Puts the negative charge on that end. Right? So when it was here, in the 2 position on the diene, it put the negative charge on the carbon closest to it. When it's here on the end of the system, it actually puts the negative charge on the carbon furthest from it, all the way on the other end. The dienophile is the same. Positive charge is going to be on this end. So it's the same argument. I'm trying to get the negative charge end of the diene, which is now this end, to together with the positively charged end of the dienophile, which is where the aldehyde is. But now that means that the aldehyde and the methoxy group are in the same position. Same thing, right? This bond is going to push over here. That's going to shove those electrons back onto oxygen. So fewer arrows in this case, but the same principle, which is we've got a resonance structure that puts a negative charge on the far end of the diene and makes the 1,2 the preferred orientation. The inverse electron demand Diels Alder reaction is very similar. The inverse electron demand interaction would have like a nitro group. Something that's electron withdrawing attached to one end. And it would have, and let me put some little time here so we can describe the things. So now we've got the electron withdrawing group. Does that lower or raise energies? What does that do to the energies of the lowers? So we've actually dropped our by 3-star orbital. This is the LUMO. And if I put my methoxy group on the plane, I put my methoxy group in the endo position where it belongs. So this is the electron donating group that raises energies. So that's actually taking pi orbital and raising it. So you'll see that now the orbitals that are close in energy are the HOMO on the diene pile and the LUMO on the diene. So that's inverse electron demand. The electrons are flowing from diene towards dienophile instead from dienophile towards diene instead of the normal, which is from diene towards dienophile. You'll notice I've drawn the methoxy group in the endo position. Why? Because we're going to get good secondary orbital overlap here between the oxygen lone pair at the back end. So for the same reason the carbonyl carbon likes to be in the endo position, so that its orbital can interact with the back end of the diene. The oxygen likes to be in the endo position. You'll notice that I've drawn the methoxy group here rather than there, so they can be in a 1,4 relationship with respect to the nitro group. The inverse electron demand has the same regiochemical preference for either 1,2 or 1,4 relationship that the regular Diels Alder reaction does. And in this case, I draw the E, right? I draw the Z isomer. This is actually the ZZ isomer because the nitro group outranks this carbon. So the methyl group and the nitro are on the same side. That's a Z, and this is a Z. So instead of E isomer, I'm looking at the ZZ isomer. What does that look like in terms of orbitals? I'll get my nitro group over here. So I've got my outer constituents. That. And then I've got my oxygen over here. Endo position. I'm now working with pi 3. That's what's here is here. Sigma symmetric orbital. And I'm working with the pi orbital here. That's the one that's the bonding interaction. It's the one that's in phase. So you'll notice that I still have the same sign on the wave function here and here, which is required to get overlap. And I've got secondary orbital overlap between this one pair and that. There's my secondary orbital overlap. So I've got the ends of the molecule interacting to form bonds. I've got the secondary orbital overlap stabilizing the transition state. That's going to cause the stereoselectivity for this methoxy group being in the endo position. Stereospecific with respect to the diene, which means these two, this methyl and this hydrogen, are going to be on the same side, which means these methyl groups are going to be trans to each other. And these two exo hydrogens are going to end up cis to each other because I can't rotate around that bond. So what's the product actually going to look like? Here it is. We've got our nitro group. I've shaded the red orbitals, right? The red orbitals correspond to the shading, so that looks like that. Here's my group there. That's going to interact with that. So I'm going to rotate these things in a this rotatory fashion. You'll notice that's putting that outer substituent down and the inner substituent up, so they're going to end up trans. There's the secondary orbital overlap between the methoxy oxygen and the back end of the group. When I rotate this, so my methyl group here and my methoxy group are going to be trans to each other. And my methyl group here is going to be on the same side. These two hydrogens, right, they're going to be trans to each other. So the methyl group is down on this end next to the nitro, up on the other end. Product is going to look like this. Methoxy group, which was endo, is going down. That. Methoxy group on the right carbon. Nitro group is over here. That carbon is still sp2 hybridized, so no stereochemistry of the nitro group. And then this methyl group that was in the outer substituent, that ends up down. This methyl group that is on the inner substituent up. Hopefully that molecule looks like this. Down on this end, up on this end, methoxy group down, the product looks like that. Why is it that the 1,4 is the right isomer? Not the 1,3. Resonance. Draw this resonance structure. Which is the electron do? They have a negative charge at the end. Double bonds to the oxygen. So that has a significant partial negative charge on it. The nitro group is pulling electron density away, putting a massive partial positive charge on that. So you see there's a positive charge here on the carbon adjacent to the nitro group. And then there's a negative charge up here on the carbon that's distal with respect to the methoxy. Again, we're getting the negative charge together with the positive charge. So if this end wants to interact with that, and that means that the methoxy group is going to be on the opposite side of the ring in the product. So it's the same argument. We use a resonance argument to talk about the regiochemistry, and we use orbital arguments to explain the stereochemistry. Stereospecific with respect to the diene, stereospecific with respect to the dienophile, stereoselective with respect to the diene versus the dienophile. It's called the Endo Rule. It means that the substituent, whether that's an electron donor or an electron withdrawing group, wants to be in the endo position. That's the Endo Rule. And then in regiochemistry, we explain this. I finished 1 minute early today. Just for your time. Getting ready to go over the quiz. So I'll post the key.